Continuing on with symmetry, we have the definition of symmetry elements, which is a point, line, or plane through which a molecule has a symmetry operation or multiple symmetry operations. So we have various kinds of symmetry elements, and I'll describe what those entail. So first we have E, something which all molecules have. You'll notice that's the same name as the operator for the identity operation, or the identity operator. So that's the identity, it leaves the molecule unchanged. All molecules have E. And we have I, which, much like the operation for inversion, is I is an inversion center. So the symmetry element I is the specific point at which you have the inversion center through which you can do the inversion operation. Then we have sigma, which is a plane of symmetry. So that's the plane through which we can execute the sigma operator, and it will leave the molecule unchanged. We have Cn, which is an n-fold axis of symmetry. So for C2, that was a 360 over 2. C2 is a 180 degree rotation. So C2 is a two-fold axis of symmetry because we have doing it twice leaves you back at the identity element. So you have to do it twice to get to 360 degrees, which is the same as the identity. So C3 is a 120 degree rotation. You have to do that 3 times to get to 360 back to identity. So it's a threefold axis, fourfold, C4 90 degrees, fourfold axis, etc., etc. Typically in molecules you don't see CNs that are more than 6, but on rare occasions they are. Benzene would be an example where you have a 6-fold axis of symmetry. And then Sn, which is an n-fold improper axis of rotation. Improper rotation axis. So as I said before, Sn is where you have something where you can perform an Sn operation, which is where you rotate by 360 over n degrees. You do the Cn operator, and then you do a sigma h. You reflect through a plane which is perpendicular to the axis that you just rotated around. Okay, so as I've been saying, we have the operation E or the symmetry element E is present in all molecules. It's present in all objects. It is the identity. You cannot escape it. It is always there. Okay, so what about something like water? We have H2O. That's obviously a planar molecule. 3 atoms can only be planar, so they obviously have to have at least one plane of symmetry. So there's the plane of the board here is a sigma. And then there's also one along this. I'm going to represent that by kind of coming in and out of the board here. So imagine that this is perpendicular to the board coming in and out. And then we also have an axis of symmetry where we can rotate around that 180 degrees there, where we have a C2 coming down there. Okay, and these mirror planes that are parallel to our axis of rotation are called sigma v for vertical. So they're vertical; they're aligned with our axis of rotation there. And there's a second one here, which we call sigma v prime. Okay, and so that's water. So what does water have? Water has E, C2, sigma v, and sigma v prime. So those are the 4 symmetry elements in H2O. Okay, what about another molecule? What about, let's see, you can do ethylene, C2H4, carbon-carbon double bond in the middle there. Okay, what does this have? Well, we have going right into the plane there at the middle. we have a C2. We can rotate around 180 degrees, leave this molecule unchanged. We also have right at the center, that point, that axis that I'm rotating around, if I put that point right in the middle of the molecule at the center of mass, that's also an inversion center. We can invert and exchange any, we can invert and exchange the atoms there, and we leave the molecule unchanged. We have a mirror plane. The molecule is planar, and this mirror plane is perpendicular to our C2, to our principal axis here, as we're going to call it. So this is perpendicular to that, so we call that sigma h for horizontal as opposed to vertical, sigma v. All right, but then there's still more stuff. There's also a C2 in this dimension. C2 right there, we can rotate this in that direction there. We also have another C2 where we can rotate, for example, in this dimension. We can rotate around there, which would exchange those two. And then there's also mirror planes in each of those as well. There's a sigma here, there's a sigma there. This is a sigma v prime, sigma h. And actually these C2s would get denoted as either prime or double prime. Okay, so a lot of symmetry elements there in ethylene. So we obviously think that that has some high degree of symmetry, and we're right because that has so many symmetry elements. And we'll see how we formally say how much symmetry that has with those given elements in a few videos. Okay, and then finally, if we want to go crazy in terms of symmetry elements, we have benzene. So benzene has, it has an inversion center in the middle there. It also has a six-fold axis of symmetry, C6. You can rotate by 60 degrees around and end up at the same points here. Then there's also a sigma h there. The molecule is again planar, so it has a mirror plane. Then there are a bunch of other elements. There's 3 mirror planes there. 1, 2, 3. We call those all sigma v. And then there's 3 more. If I can find a good color. I'm running out of colors. Lots of operations to do here. 3 more mirror planes there, there, and there. Those are called sigma d for dihedral. I'll explain that in a second. And each of those also has C2s around it as well. So each of those has a C2. And then that's actually called C2 prime because there's a C2 operation within that C6. The C6 cubed is C2. Okay, and then there's around the sigma d's, there's also C2. So that's C2 double prime. So lots and lots of symmetry operations with benzene. There are actually 24 there, or symmetry operations, there are 24 there. And for this ethylene, there are 8. So we can see we're kind of going more and more symmetric there, and we'll have that formally described in a little bit. Okay, so what are some of these things that we've described in this process? So we have a Cn with the maximum N. That's called the principal axis of the molecule. So in the case of water, that was the C2. That was a C2 here in ethylene, and that's the C6 here in benzene. So the principal axis is the Cn with the highest N, or the smallest amount of rotation, whichever you prefer to look at it. We have sigma h, which is perpendicular to the principal axis. So I called this sigma h here because it's perpendicular to the C2 I've defined as the principal axis. These are both CV because they are parallel to it. This sigma h here is perpendicular to C6. It's in the plane of the board. Okay, and we have sigma v, which is parallel to the principal axis. And the last one I described, which is kind of the most confusing one, which is sigma D, which it bisects the C2, which is perpendicular. That symbol for perpendicular, that kind of upside down T, is perpendicular to the principal axis. And that D stands for dihedral. V for vertical, sigma H for horizontal, sigma V for vertical, sigma D for dihedral. So we have our principal axis C6 here. We have our C2s, which are perpendicular to that, and then the sigma Ds are the mirror planes that are bisecting those C2s. Even though they have their own C2s, but we've referred to those as C2 double prime. We've referred to them as inferior to the C2 prime or the sigma V. Okay, so those are some examples of symmetry elements, and again, there will be more practice and examples to come.